3 concentric rings of mountain ranges surround Mare Orientale, and some of the peaks rise to several thousand feet. They're all effects of the monster impact.
When we see mountain ranges on the Earth, they're mostly caused first by the continents moving around, crashing into each other very slowly, buckling up and creating mountain ranges, which then erode into all the spectacular shapes that we see, the Matterhorn and so forth, from water erosion.
On the Moon, there are no continental plate tectonics. The surface is static.
Yet you still have mountains on the Moon. And the reason is that those big impact basins, that's a big explosion, excavates a pit, throws material up on the outside. So you have these rings of mountains, arcs of mountains that surround the impact sites. But they're impact features. Again, they're caused by the external forces, not the internal forces.
Another notable impact crater, much smaller than Mare Orientale, but every bit as spectacular, is Tycho. Named after a prominent 17th century Danish astronomer, this impact feature is located in the southwestern quadrant of the Moon's near side.
It's in the bright area. You can almost see it with your naked eye. And when that explosion happened, as with many other craters, it shot out jets of bright, powdery dust. So there are these rays that go out from it. It's very striking.
The rays of dusty, ejected material extend some 900 miles from the Tycho impact site. A mountain of debris also rises from the center of the crater. This is a result of recoil from the asteroid strike. Some of the highly compressed material at the center of the impact site springs outward once the impacting body either ricochets or disintegrates. But long before any of the Moon's specific features could be discerned through sophisticated telescopes and space travel, careful observation of lunar behavior and appearance was still vitally important to Earth dwellers. For 15,000 years at least, man revered the Moon as a source of light, as a navigational guide, as a reference in agricultural pursuits, and most of all, as a convenient timekeeper. In the days before our modern systems, timekeeping was no simple task. Early timekeepers had 2 choices. They could monitor the sun or the moon.
If you think about trying to keep track of dates, if you use a solar calendar like we do nowadays, there are 365 days in a year, and that's an awful lot of days to keep track of. And it's not something that the ordinary person can do very well. Compare that with a lunar calendar. Everybody can tell when the full moon is, when the new moon is. You don't see the moon at new moon. You see it, it's big and round at full moon, so it's easy to tell. There are only 28 to 29 days in a lunar cycle, so it's easy to count them. And so most societies actually start out with a lunar calendar.
Early observers of the Moon also recognized that our planetary neighbor has a very real physical effect on the Earth itself. The Moon is responsible for the rise and fall of our ocean tides.
If we think of the Moon as being this tennis ball and the Earth as being this football, okay, the tides are caused by the Moon's gravitational attraction. So it's obvious, okay, so the Moon kind of pulls the Earth's water towards it. And so this creates a slight bulge in the direction of the Moon. What's less obvious is there's also a bulge in the direction away from the Moon. So there's, in fact, 2 high tides every day. The other high tide you can think of as being caused by the Earth's centripetal force. The Earth and the Moon are both rotating around, and that causes the water on the far side to also move out.
An extreme illustration of the difference between high and low tides can be found along the shore of Canada's Bay of Fundy. The water level from high tide to low tide drops an astounding 55 feet. For some forms of life on Earth, the advance and retreat of the tides creates useful habitats. But another of the Moon's gravitational effects on our planet is directly responsible for nothing less than the continued survival of terrestrial life itself. The Moon stabilizes Earth's climate. The gravitational effect of the Moon keeps the degree of tilt in the Earth's rotational axis constant. This tilt is what maintains the repeatable cycle of seasons as the Earth orbits the Sun.
If we didn't have the Moon, or if we had a much smaller moon, for example, then you can mathematically show that the tilt of our North Pole would vary widely, with that angle going from, say, 0 to 90 degrees. Currently, it's 23.5 degrees. And it would actually vary chaotically. And so the Moon has played an important role in the stability of our axis of rotation of our planet, and therefore in our climate.
Over the millennia, with the Moon's prominent and constant presence in our night sky, men ultimately began to speculate on its origin. How did it form? How did the Moon come to be? In 455 BCE, the Greek scholar Anaxagoras theorized that the Moon was simply a rock that was flung off by the Earth. Most of his contemporaries, on the other hand, were convinced that the Moon was a god, or maybe a huge ball of fire. So Anaxagoras' notion did not get much traction. Quiet speculation no doubt continued, but no hard information about the Moon came until 1609, when Italian astronomer Galileo Galilei pointed one of the first telescopes at the Moon and recognized that he was looking at a landscape, the terrain of another world.
When you look at the Moon through a telescope, it looks completely different from the way it looks to the naked eye. Instead of looking flat the way it does to the naked eye, it really looks round, and you can see the shadows, you can see all these craters that the naked eye does not see, and it just immediately looks like a world. It jumps out at you into 3 dimensions.
Galileo made detailed drawings of the small planet's surface and established once and for all that the Moon is a solid world, not a god or a fireball. But the groundbreaking astronomer never publicly speculated on the Moon's origin, primarily because his interests soon moved to other planets. Not until 1873 did the first science-based theory regarding the origin of the Moon publicly emerge. It sprang from the mind of a talented French astronomer named Edward Roche.
Roche advocated what's called the co-accretion theory, which says that basically Earth and the Moon grew up at the same time out of the same materials.
In Roche's day, many scientists began to believe that the planets might have formed from hot condensing clouds of gas.
It gradually contracted and cooled, and as it contracted, it would separate out rings of gas. So you'd have a ring of gas here, a ring here, and so forth. And these rings of gas would then eventually coalesce and form the planets.